Hi, Richard Walding here again. I'm just going to have a look at a fairly straightforward piece of the syllabus. It's called particle interactions. It's the last topic really in Unit 4. Now I'm going to divide it up into two parts. I'm going to divide it up into 14. This is chapter 14.1 in the textbook, this textbook here, page 374-75, but it's fairly general. It applies to all textbooks would have the same sort of thing. So 14.1a, I'm going to have a look at Baryon and Lepton numbers, and then 14.1b, I'm going to have a look at what's called the conservation laws related to those two. It's pretty straightforward, but I've divided it up just to give you a bit of a breather. Now, in the syllabus, all they ask you to do is to define the concept of Baryon and Lepton numbers. Now, what do they mean by define? It's not to state or recall. It's a little bit more than that. So you're going to state the meaning of it and identify or describe some of the qualities. So it's a little bit more than just recalling the formula or something like that. Now, typically in a mock exam, they'd probably ask you to define the concept of a Baryon number or a Lepton number in terms of what's in the syllabus. They certainly won't get you to do any calculations. They actually say that no calculations are needed. But so this is what I'd do. I'd define. Let's have a look at Baryon number. Now I've got to get the words right here. Strictly conserved. The additive quantum number defined by. Now I'm going to write the formula down here in a second, but so this is Baryon number. It's a symbol B, so it's Baryon number is B, a strictly conserved additive quantum number defined by so and so. Now I'll put down the formula. It's just B equals 1/3 of the number of quarks minus the number of antiquarks. Now, if I were you, I'd learn that off by heart. Learn that statement off by heart, and that's basically all you'd have to do, apart from describing what these numbers mean. And what I'd do is have the next paragraph that'd say where B equals Baryon number, NQ equals the number of quarks, and NQ with a bar over it is the number of antiquarks. Okay, that's all you'd have to do. Now, if they said define the two of them, I'll do Lepton number in a minute, but it's much the same. That'd be your 1 or 2 marks for that, so it's pretty straightforward. Now let me have a look at, just to get you familiar with what it means. I mean, all you have to do is repeat that basically, and you've got your couple of marks. But it's, you really want to know what it means rather than just having the words written down. Strictly means it's always obeyed, right? So it's a conservation law, if you like, that's always obeyed. Not sometimes, not 99% of the time, it's always obeyed. So strictly means always. Conserved means what you start with is what you end up with. It's a Latin word meaning that there's no change in the substance or the article or whatever it happens to be. So for instance, you might have heard of like jam conserves. In other words, it's a way of preserving the fruit, so the fruit doesn't rot away and turn into something else. So conserved means basically not to change. Additive means you can just add the numbers together. Quantum number just refers to this unit on quantum physics, defined by the formula and so on. So let's have a look at this formula with a couple of different particles. So it refers to particles that are going to interact, subatomic particles really. So let's have a look. I'll just get rid of all of this and we'll just have a look at a couple of examples. So here's the formula again. B equals 1/3 NQ minus NQ bar. Okay, and look, I'll put some particles here, and I think we can have a guess at what B will be, and then I'll use the formula to say it. So the particle, let's start off with a proton, for instance. So P plus. Now, you know that a proton is a baryon, so it should have a baryon number of 1. So let's try this and see how it works. Now let's apply the formula. Now you know a proton is made up of an up, up, down quark. Now you'd be really wise to remember the quark breakup, or the quark composition of protons and neutrons, and maybe a meson, just one meson, but you'd need that for the last section, which is on Feynman diagram. So I say to my students, just learn it off by heart, what a proton is and what a neutron is. So let's have a look. The formula will be 1/3 of NQ, the number of quarks, so there's 3 quarks, minus the number of antiquarks, which is 0, and that comes to +1. So that makes sense. Let's have a look at a neutron, which is an up, down, down, and it's a baryon as well, so presumably it'll be +1. So it's 1/3 of 3 quarks minus 0 antiquarks, and that's +1. Yep. Okay, what about a antiproton? Now that'll be an anti-up, anti-up, and anti-down. Okay, now you're expected to know what an antiparticle is. It has the same properties or the same mass as the particle. So antiproton has the same mass as a proton, but will have opposite charge. In other words, the quarks are all the antiparticle, all their opposite charges. Now you could also write this as P minus if you like, because that's P plus. This will be minus, but you could write it with a little bar over the top. So if you had to guess, you'd probably say, well, the baryon number is probably the anti-version of that, and so it'll be 1/3 of number of quarks, 0 minus 3, and that's -1. And the same would happen for an anti-neutron. So an anti-neutron would be anti-up, anti-down, anti-down, guessing -1, and it'll be 1/3 of 0 minus 3, which equals -1, and they agree. Now look, just to try a couple that aren't baryons, let's say we tried a meson. Now you know a meson, I'll write it here so you don't forget, is a quark anti-quark pair. Now that could be an up and an anti-up, or a charm and a strange, anti-strange, or whatever. It's just 2. They don't have to be the same, but one has to be an anti-quark. Now it's not a baryon, so let's guess that it'll have a baryon of 0. So it's 1/3 number of quarks, 1, number of antiquarks, 1, 1 minus 1 is 0, 1/3 of 0 is 0, and sure enough, it agrees. Now there's no such thing as an anti-meson. Well, there could be, but you'd have it's still I shouldn't say you can't have it. You end up with an antiquark and a quark as well, depending on the flavour of the quark, you know, whether it's up, down, or whatever. You'll get a different combination, but it'll still be it'll still be a quark and an antiquark. Look, let's try one more. Let's try something like an electron. Okay, you'd guess it's not a baryon, so it'll have a baryon number of 0, and sure enough, 1/3, 0 minus 0 is 0. There's no quarks in it, there's no antiquarks. Lastly, what about, say, a antineutrino? It's certainly not a baryon, so it's 1/3 of 0 minus 0, and that's 0. Tick, tick, ta-da, we're all done. So all of that seems to make sense. So if I were you, I'd learn that definition I had there, and maybe an example of one. You wouldn't have much, but remember I said it's about describing the qualities of the concept. So the syllabus says, describe the concept of baryon and lepton numbers, which means you state the meaning of it and you describe its qualities, or identify or describe its qualities, which you could easily do with one example. Okay, just that. That's it. Okay, let's move on to lepton numbers. And now, lepton numbers are almost the same idea. So, look, I'll just get rid of this so you don't get confused. And we'll say lepton numbers, or a lepton number, L, is, now it's strictly conserved additive quantum number defined by, and the formula is just L equals the number of leptons minus the number of anti-leptons. Okay, so there's no thirds or anything like that. It's just straight out the difference between the two. Now just be careful if you're trying to say this in words, you get into a bit of a tangle. Because if you go back to baryon number, if you tried to describe that formula in words, you'd say it's equal to a third of the number of quarks minus antiquarks. Now what you mean is the third of everything that followed, the quarks minus antiquarks. But it almost sounds like a third of the number of quarks minus the antiquarks. Okay, which would be tricky. You want to say brackets, but you can't use it for words. So that's where a formula is so much more powerful. And when you say the difference, you've got to be careful. It's not the difference, because it's the leptons minus the anti-leptons, right? It'll have a plus or minus value. So it's more than just a difference. So what you'd say for lepton number, strictly conserved additive quantum number defined by this formula here. Now, that's not in the syllabus in the content objectives. You'll find it in the definitions. Your teachers might have given it to you, but it's in the definitions for lepton number. You'll see it like that. Okay, let's have a look at a couple of examples. For instance, an electron. Now, you'd guess that an electron, it's the most famous of all the leptons, so it'll have a lepton number of, you'd think it'd be 1. Don't get confused by the minus sign. This is where students often get it tangled up, and I keep stressing, be careful with the signs for lepton number. Okay, so it's equal to the number of leptons, which is 1, minus the number of anti-leptons, 0. Okay, so it's basically, what am I saying? It's got a lepton number of 1. Okay, now you could do that for a positron, which is an anti-lepton. It'd be number of leptons is 0 minus 1 because it's an anti-lepton. Okay, so I'll put a positive in there because that would be positive. This will be negative. Now what you'll notice is that the electron has a lepton number of +1, and the positron, or the anti-electron, which has a positive charge, has a lepton number of -1, and students get into a bit of a tangle. Luckily, you won't be asked to do any calculations on the exam. It's, the guidance in the syllabus is you won't be expected to do any calculations on that. Okay, but I'm not quite sure how they'd word a question where they might say somehow that which of the following fits the pattern for the formula. It could be something like that. I'm not sure. I don't think it's going to be anything much because it's basically just a 1 mark thing. It doesn't get much of a mention in the syllabus. I think the next part, which is on the conservation of baryon and lepton numbers, is probably where you'd get a mark. Look, let's try something else. A proton, for instance, no leptons. Well, you'd expect it's a baryon, it's not a lepton, so you'd expect it to be 0. So the number of leptons in that is 0, the number of anti-leptons is 0, and so on. A neutrino, or let's say an anti-neutrino, number of leptons is 0, number of anti-leptons, so it's -1. And maybe I should do a neutrino, electron neutrino. It's a 1 minus 0, it's +1. Okay, so that's about all there is to that. I'll come back when I do the conservation laws. We'll look at these numbers again, but just be careful. You don't have to do calculations on it, and you don't have to do calculations on the conservation laws, which is coming up in a second. It's just purely to define the concept of baryon numbers. Use that statement I said, put the formula in, and maybe give one example. That's all you'd be expected to do. I think I might leave it there. Okay, I'll see you in conservation laws in a minute.